With the concept of law of total probability, we are now ready for Bayes' theorem. Why do we want to learn Bayes' theorem? The Bayes' theorem is useful when we want to revise our estimation of an event's probability after additional information becomes available. For example, suppose a city has 55% male and 45% female. Among the males in the city, 15% of them have a college degree. Among the females in the city, 17% of them have a college degree. Let event A be male. Then we can define event A complement to be female. Next, we define event B as having a college degree. Then we can see that we have the probability of A, the probability of A complement, the conditional probabilities of B given A, and B given A complement. However, what we are interested in is the conditional probability of selecting a male citizen given that this randomly selected citizen holds a college degree, which is the probability of A given B, the reversed conditional probabilities of the two events. In this example, probability of A and probability of A complement are called prior probabilities because they are determined prior to knowing whether a person has a college degree. The conditional probabilities of B given A and B given A complement are the likelihoods that a person has a college degree by gender. The probability of A given B is called the posterior probability or revised probability because the prior probability of A is revised after knowing whether the person has a college degree. Bayes' theorem allows us to calculate the revised probabilities or posterior probabilities to improve our decision when we have new information. The revised probability is usually an unknown conditional probability. When we have the prior probabilities of the event and the reversed conditional probabilities of the event we are interested in, then the non-reversed conditional probabilities can be viewed as the additional information that allows us to convert the prior probability to a posterior probability, such that we have a better estimation of the event that we are interested in. Let's go back to the same example. We see that event A and A complement form a partition of the sample space, and we know their probabilities. We also know the probabilities of B given A and B given A complement. With this information and the additional information that event B has occurred, we want to calculate the posterior probability of event A given B. By definition, probability of A given B is calculated by probability of A intersect B divided by probability of B. We can apply law of total probability to find the bottom part of the equation. And use multiplication rule to find the joint probabilities. Therefore, we can get the answer by plugging in the numbers into the equation, and then we can find the probability of A given B. Next, let us see one more example to illustrate why it is important to learn Bayes' theorem. Read this problem description, and before you calculate an answer, use your hunch to guess a range of the probability. You can pause the video to read the information. When you are ready, resume the video and see if your hunch is accurate. From the problem description, the 85% green and 15% blue caps are the prior probabilities about a taxicab's color. The additional information is that the witness has identified the cab as a blue cab, and the court has the conditional probabilities for the witness reliability. And the probability that we are interested in is the revised probability when we learn that the witness has identified the cab that involves in the hit and run accident as a blue cab. Therefore, we can apply Bayes' theorem to this problem. We want to know the probability that the taxicab is indeed a blue cab, given that the witness says that it is a blue cab. The first line of the equation is obtained by definition. We apply multiplication rule to the top part of the equation. And we apply law of total probability to the bottom part of the equation. Then we can find the revised probability to be 0.4848, which means that there is less than 50% chance that the taxicab is a blue cab, even though the witness says that it is a blue cab. Are you surprised by the answer? I know some of you are. If you ask this question to people who have never learned Bayes' theorem, most of them will guess a probability that is higher than 50%. The main reason why this probability is so small is because there are much more green cabs in the city than blue cabs in the city. If we ignore the prior probabilities that there are relatively few blue cabs in the city and only focus on conditional probabilities for the witness reliability, then we might be misled. Still, the revised probability is 48.48%, which is much higher than the prior probability of 15%. It is just not as high as many people would think using their hunch. Human beings very often use heuristics to make judgments. This example is used to highlight that learning probability can help us make more objective decisions when we might be biased by our heuristics or hunch. The next two slides are used to illustrate two additional methods that can be used to calculate posterior probabilities. I will not read through the slides. You will find that you still need to apply law of total probability to find the denominator in calculating the posterior probabilities. Next, I would like you to try an example on your own. Pause the video to work on the problem. You can resume to see how I solve the problem when you are ready. First, we see that N has 3 transportation modes. These 3 transportation modes form a partition of the sample space. We also have the information that N is late. From the problem description, we have the prior probabilities of the transportation modes. We also have the conditional probabilities that N is late given the 3 transportation modes. Now, we want to know the probability that N takes a bus, given that we know that she's late. We start with the definition. The top of the equation can be calculated by multiplication rule. Probability that N takes a bus times the conditional probability that she is late when she takes a bus. The bottom of the equation is calculated by law of total probability. In particular, the probability that N is late is the conditional probabilities that she is being late weighted by the probability of the transportation mode. Then we can obtain the final answer. Here are the takeaways of the 2 advanced probability rules. I encourage you to try more exercises on your own.